What's up, pre-calculus students? We are going to do our 50 select review questions from the reviews in order. That way you don't have to look them up. Goal for you guys is to do these in 100 minutes, 2 minutes per question. Your test is 40 questions in 80 minutes. I'm going to try to do these 50 questions in 50 minutes. So I'm going to kind of breeze through them. This is not a satisfactory review. These are just example problems. If you want to really review everything, you got all of your quiz A's in the Schoology folder. You have the scramble quizzes that we've been doing. You got to know everything. It's a even distribution from all of our units besides unit 0. There's like nothing in unit 0, but we're going to review it anyways. Even distribution of questions from 1, 2, 3, 4, and 5. A little bit more in 4 and 5 than 1, 2, and 3. It's 50% 1, 2, and 3, and 50% 4 and 5. All right, here we go. 50 minutes, 9:07. We're going to be done by 9:57. Ready, set, go. F of 0, I'm replacing x with 0. I got 4 times minus 2 times 5, so that's 4 minus 10, that's negative 6. When is f of x equal to 0? 4 minus 2 times 5 minus x equals 0. I'll subtract. I'm going to distribute. Yo, if somebody finds a mistake, I will give you an extra bonus point on your midterm. 1 bonus point. And it's the first person who finds a mistake. So I'm going to try to not make any mistakes. Which means I'm going to go back and check. 3. 5 minus 3 is 2 times negative 2 is 4. 4 plus 4 is 0. 5 times 2 is 10. 4 minus 10. 4 minus 10 is negative 6. Four minus 22, negative 18. When does w of x equal 2? Going to move everything onto the same side. Trying to factor two numbers that multiply to get 2 and add to get 2. Doesn't exist. Completing the square is an option. Quadratic form is an option. X equals the opposite of b. Plus or minus, or b over 2a. I like to do it this. Plus or minus, I like to do it this way. Square root of b squared minus 4 times 1 times negative 2. 4 times 1 times negative 2 is negative 8. That becomes 12 all over 2a. So this is negative 1 plus or minus. This is root 4 root 3, which is 2 root 3 over 2. So this is negative 1 plus or minus root 3. When does x squared plus 2x equal negative x squared minus 1? That's when 2x squared plus 2x plus 1 equals 0. Same deal. Backup is always quadratic formula. Opposite of b over 2a plus or minus b squared minus 4ac. 4 minus 4 times 2 times 1. That's 4 minus a, which is negative 4. Okay, that's the difference. All over 2a. Giving me negative a half plus or minus 2I over 4, which is negative a half plus or minus I halves, or 1/2 I. Vertex or W. Yo, I know W can be factored as x times x plus 2, which means I have zeros at 0 and negative 2. Since quadratics are symmetrical, you know the vertex is smack dab in between. X equals negative 1 is the x location of the vertex. The y location would be negative 1 squared, minus 2, negative 1, negative 1. These are long questions, by the way, these first questions, so I'm probably running behind schedule. X equals 3, x equals negative 2 are the zeros. The average of those two is the x-coordinate of your vertex. That's like the midpoint. Midpoint's the average of the two numbers. Plug those back in to find the y-coordinate. I don't want to do that, but I'm going to. H of a half is 2 times 1/2 minus 6 halves, 1/2 plus 4 halves, 2 times negative 5 halves times 5 halves. Cancel, negative 25 halves. 2, x minus 3x plus 2 equals negative 11. Regardless if this is important to do, these questions, like the most important questions, start at question 6. It's good algebra, it's good practice. The only way to solve this equation is to distribute everything and move everything on the same side. So I have 2x squared minus x minus 6 because I know how to distribute. If you don't know how to distribute, that's a problem. Write it out. Use a box. Don't ask me. It's like, is this the box? Don't ask me that. Be like, we're just multiplying. I'm adding 11. That becomes a minus 1. And then I'm using the quadratic formula again. X equals the opposite of b over 2a plus or minus the square root of b squared minus 4 times a times c. That's negative 8. 4 minus negative 8 becomes another 12 all over 2a. So that's 2 root. I feel like this is the same question. 1/2 plus root 3 over 2. F of 8 is 4. What is f of negative 4? Well, if f of 8 is 4, when I plug in 8, I should get 4. Just take anything from the table towards the back. Subtract 6, I get k is negative 2. And now f of negative 4 is negative 5. X equals plus or minus 5i. Subtract 25 square root. X plus 3 squared equals negative 4. I don't have to distribute everything because I could just square root both sides. X plus 3 equals plus or minus 2i. X equals negative 3 plus or minus 2i. You could write it as plus or minus 2i minus 3. I'm going to divide by negative 2. Going to subtract 1. Take the opposite of both sides. And then we talked about how you use a reciprocal power to solve rational exponent equations. What is 8 to the 2/3? We did this so many times that we should be able to do it by now. At the beginning of the year, you guys stunk at this. This is 8 to the 1/3 squared. 8 to the 1/3 is 2. 2 squared is 4. There's your answer. All right, here we go. Unit 1. Graph function models the percentage of charge in a phone battery based on the graph, which is the following conditions and statements about the function is accurate. C is decreasing consistently. C is always decreasing. As time increases, the charge of the battery is always decreasing. Yes. The charge is decreasing at different rates. Concave up means it's decreasing at an increasing rate. This is decreasing at a decreasing rate. This is decreasing at an increasing rate. So the charge is decreasing at different rates. Okay, boom. One question, 1 minute. I'm going to go ahead and say this. I don't like this question because we don't know what's happening in between the points. We're just going to assume like this is a polynomial. So let's look at some rates of change. I'm going to subtract 10, divide by 1. I'm going to subtract 12, divide by 1. Subtract 14, 39, 49, 53. Subtract 16, subtract 18. So these are my rates of change. They are negative. That means f is decreasing. Let's look at the rates of change of my rates of change. From negative 10 to negative 12, I subtract 2. Negative 12 to negative 14, I'm subtracting 2, subtracting 2, which means the average rates of change of f are decreasing, which means we are concave down. Why? Because the average rates of change are decreasing. If you graphed it 17, 27, 39, 53, you're like decreasing at a decreasing rate. You think it's getting faster. A lot of people will make mistakes on this. They will say, oh, it's going faster downward. That means the average rates of change are increasing, but no, they are decreasing. Negative 10 to negative 12, minus 2. I have to stop explaining because we just have to get the answers. At point A, well, I am increasing at a decreasing rate. It looks like the graph is going to be concave down all the way to here. And then this is where the graph is concave up. And then we switch to being concave down again. So I think we're increasing concave down. We're increasing at a decreasing rate. So the average rate of change is positive because we're increasing. If your rate is positive, your original function's increasing. If your rates are increasing, your original function's concave up. We're concave down. Sorry. Increasing, concave down. See. Average rate of change is negative. That means the slope of the secant must be negative. Must be there. The slope must be negative. So we're talking about, on average, the function must be going down. Not true here. Not true here. Not true here. Must be true here. That slope is, on average, how quickly the function is changing in a y's per x. I use Desmos for this. You're not using your calculator at all. This is more just questions that make you have to know increasing, decreasing, concave up, concave down stuff. So using Desmos would be a lot quicker for me. All right, cool. Coordinates of the local streama of f, we have a min at 0.739, negative 8.832. The zeros are at negative 1.6 and 1.4. This is why Desmos is so easy. Like, it knows the interesting points of the function and just gives it to you. F of 1 negative 7.8. When is f of x equal to 6? Your goal is to do this with a calculator. Was the function decreasing? It looks like we're decreasing for all x's until 0.739. So when x is less than 0.739, we are going down. Here are points of inflection. Okay. So let me just kind of label these. Negative 0.813 is that actual point right there. That's a point of inflection. And 0.2 0.213, which is right around there. Okay. When we concave down, it looks like we're just concave down to here. So between my points of inflection, it's between negative 0.813 and 0.213. What is the rate of change increasing? Now remember, rates, positive, original function increasing. Rates increasing. If the rates are going up, slopes of 0, 1, 2, 3, 4, 5. My original function is concave up. Okay? It's confusing. When the rate is increasing is when the function is concave up. These rates, negative 5, 4, 3, 2, 1, are increasing. So from negative infinity to negative 0.813, we are concave up. My rates are increasing. And then from 0.213 to infinity. So the rest of the interval. What's the average rate of change? Watch. I need to find the slope. I will do f of 3.4 minus f of negative 1.2 over 3.4 minus negative 1.2. 87.44. That's crazy. You use a slope to find a rate of change. One's the function negative between my two zeros. That's between negative 1.6 and 1.4. All right. Unit 2. P of x. We're bouncing off of negative 3 and 2. So we got multiplicities of 2, just like x squared. So negative 3 and 2 are zeros. There we go, D. As our input values decrease without bound, as I go to the left, this is a cubic. Its end behavior is down and up, just like x cubed's end behavior. It is a positive leading coefficient. So my outputs are decreasing without bound. It is known that as my inputs decrease without bound, my outputs decrease without bound. And as my inputs increase without bound, my outputs decrease without bound. You have to be able to interpret these limit statements. If these are confusing to you, you never really learned anything. What does this mean? This function has to be a negative even. A must be negative. B must be even. wait, because as x increases outbound or decreases outbound, the end behaviors are different. That's not true. The end behaviors are the same. A must be negative, but B must be even. Because as x increases without beyond or decreases, the end behaviors are the same. All right. So it's really that you have a negative x to the even, but this is the correct answer. Okay. We have a negative x to the fourth. We have to have a maximum. There has to be some point where there's a max. Now let's see. I'm going to factor some stuff out. I'm going to factor out a negative x squared, and I get positive x squared minus x minus 20, which factors to be x minus 5, x plus 4, which means I have a 0 at negative 4, I have a 0 at 5, and I have a 0 at 0, and it's going to bounce. I'm going to pass through here. I'm going to bounce off of here. I'm going to pass through here. Now, this is a tricky question, and I don't like this question. I probably should not have asked this question. But the idea is that since there's more space between 0 and 5, and this is a polynomial, you have more time to go up and then down. I believe the answer is going to be a global max between 0 and 5. I'm just going to double check this just so I'm not wrong. If I graph negative x to the fourth plus x cubed plus 20x squared, we should see what? Yeah, a lot of them are. Yeah. So you have to get the right answer. You should see, yep, a maximum between 0 and 5. I don't love the question. Probably just understanding you have a global maximum is better for me. 3 zeros. It's an x cubed. No overall maxes or mins. 3 zeros at negative 1, 2, and 3 mean 2 relative maxes and mins. We got a min, we got a max. That's not right. 3 zeros, 2 extrema, no global extrema. No. 3 zeros, 2 local extrema, no global extrema. End behaviors, if I go to the left, I'm going up. If I go to the right, I'm going up. I need to have some positive x to the fourth or even, really. This is going to be an x cubed. This is 1, 2, 3. This is going to be a positive x to the fourth. That'll be a negative x cubed. That'll be a negative x to the fourth. Imaginary solutions, complex solutions have to come in pairs. You have to have a plus or minus imaginaries. So 0 means x is a factor. 5 means x minus 5 is a factor. 3 minus 2i means 3 minus 2i and 3 plus 2i have to be factors. This is a possible expression. Okay, cool. Polynomials and behavior done. Rational functions, don't forget, possible sign changes occur at zeros and at undefined, vertical asymptotes. This is a vertical asymptote. I have a 0 here. If I plugged in test points, I'd see the signs. What does that mean? I could also look as x approaches infinity and see that I'm approaching 1, which means my graph probably looks like this. This is y equals 1. This will come through this negatives to positives to y equals 1. What are we positive to the left of -5 and to the right of 3? Zeros are at -4 and 3. Zeros occur. A lot of people really screwed up on this unit. So zeros occur when you have a 0 in the top, not in the bottom. This one's a possible one. This one's a possible one. But you have a 0 on the top and the bottom. It's got to be B. Okay. One-sided limit notation. You need to review this. To the left of -1. To the left of -1. My function is going down towards negative infinity. That's wrong. To the left of -1. That's wrong. To the left of -1. That's it. I don't have to check any others, but that one's good. All the rest of them work out good. How do you determine end behavior? Well, we're thinking about what happens if I plug in infinity. Well, if I plug in infinity, I don't care about the -5x and the 3 and the 6. This is similar to polynomial end behavior. We just care about the largest degree term. It will dominate what's going on in the numerator and denominator when plugging in big values. The rest of it will be like adding small decimals to very, very large numbers. So I just care about x squared over 2x. And I realize that that's really the same as x over 2. This rational function's end behavior will be the same as y equals 1 over 1/2 x's end behavior. Now, we do have a slant asymptote. I wish they had x over 2. I don't know why they don't have x over 2. There is a slant asymptote. We could find the exact equation of that slant asymptote if we divided the two equations. They're not asking you to do that, so I'm not going to. The degree of n is less than the degree of d. If the degree of n is less than the degree of d, then really what's happening, whether it's something like this or something else, is that as you plug in values that are getting larger and larger and larger, this is trending towards 0, which means I have a horizontal asymptote. My end behavior is 0. My end behavior should be y equals 0. That's end behavior is not y equals 0. It looks like there's a slant asymptote. This end behavior looks like it's at a different value. This has end behavior that's going in different directions, whether it's going up to the left or up to the right. This is the only one whose end behavior is y equals 0. Vertical asymptotes occur when you end up with a number over 0. Why? Because as we get close to plugging in the value where you get a number over 0, you'd have a number divided by something very, 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 very close to 0. This might be positive or negative. This might be positive or negative, which means the result might end up being a positive or a negative infinity as I get close to plugging in. This is why we're talking about using limit notation. So anyways, as we get close to that, we get the result. But at the location, what you'll find is you'll get a number over 0. So you want a 0 factor in the denominator that does not exist in the numerator. Or there's more of them in the denominator than the numerator. For example, like x minus 2 can cancel once, which means I still can't plug in 2. I'd get a number over 0. X equals 2 is 1. X equals -1 is not. If I plug in -1, I'd find that I'd have a hole. I have 0 over 0. So it's tough to see. You would think we have holes at 2 and -1, but it's the fact that I still won't be able to divide by 0 makes 2 a hole. 0 is also going to be still can't divide by 0 makes 2 a vertical asymptote. We'll be able to plug in -1 after simplifying means -1 is a whole. Can't plug in 0 at all. You get a number over 0, vertical asymptote. So 2 and 0, tricky question. All right, I want the factors x minus 2, x minus 4 in the denominator. That's x squared minus 6x plus 8 in the denominator. As x gets close to 1, my y's will get close to 2. At 1, I don't have a point. If I plugged in 1, I'd get 0 over 0. That's the idea of a hole. But holes have limits. As I get close to 1, I'm going to get close to a half. This is not correct. This is not correct. As I get close to 1, my limits, I will get close to a half. They're defined, but these, no. As I get close to 1, these values are getting closer and closer to 1/2, which is why the limit as x approaches 1 equals a half. To the left of 1, I'm getting something close to a half. To the right of 1, I'm getting something close to a half. As I get closer and closer to 1, my y values get closer and closer to a half. Definition of a limit. Holes, 0 over 0, but same multiplicity. Actually don't have a hole at 1. I have a hole at 0. Why don't I have a hole at 1? Because if I cancel one of these zeros, x minus 1 and x minus 1, I still have an x minus 1. I'll still have a 0 in the denominator. What I did in my class is like if I plugged in 1, you'd have 1, 2, you'd have 0, you'd have 1, you'd have 0 squared. If I cancel one of these zeros, I still have a 0 in the denominator. So x equals 1 is actually a location of a vertical asymptote. However, if I plugged in 0, I'd have 0 squared, 1, negative 1, 0, negative 1 squared. Well, like that cancels with that, which means I end up with a 0 over a number, which means I have a hole at 0. I don't have a hole at 1. Slant asymptotes. Divide. I'm going to use synthetic division because it's easy. Use the root. Using the root enables you to add. Drop this guy down. If you want to use, this is the remainder. This is your numbers. This is your x's. Now this is important. 2x squared minus 5x plus 3 over x plus 2 is equal to 2x minus 9 minus 8x plus 2's. As x approaches infinity, this goes to 0. This would be our end behavior's equation. Just that. Okay, notice we don't have the extra stuff. The extra stuff shows the equivalent form of our rational expression. Fun. If I plugged in 3, what do I get? 5 times 2 times negative 1 over 5 times 6 times 2 times 0. Okay. I'm going to get a number over 0, which is my indication of a vertical asymptote, which my indication is I'm going to get a positive or a negative infinity as my answer. Now I need to pay attention to the signs. So I'm actually going to do a very small sign analysis around 3. I'm going to plug in something close to 3, like 3.5. I don't want to plug in 4 because it's too far. If I plug in 3.5, positive, positive, negative, positive, 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 Boom, that'll be a negative, that'll be a positive. If I'm to the left of 3, I'll be trending up towards positive infinity. I bet you a lot of you had no idea what to do here. If I'm to the right of 3, I'm trending down towards negative infinity. All right, we just dealt with a vertical asymptote. If I plugged in 1, I get, and this is the key, guys, plug in your value first, see what you get, and then do further analysis. If I plug in 1, I get 3, 0, negative 3, 5, 4, 0, negative 2. Yeah, I got a hole. 0 over 0. I have a hole. What would happen if I canceled the zeros and we didn't have to worry about having that factor? Well, I'd get negative 9 over negative 40. That's the location of my hole. That is what I would be approaching to the left and right of 1, no matter if we're 1 to the left or 1 to the right. We don't do a sign analysis here. I'm approaching this y value. If the zeros were gone, this is what I'd have. If the factors were gone. Same on the right side. I don't have to do a sign analysis. I just get this as my answer. Four to the left. If I plugged in 4, I get a 0 on the top and a number on the bottom. That's going to be 0. If I plugged in 4 to the right, I'm going to get 0. Don't plug in 3.9999. Think about it. But start with plugging in 4, see what you get. If I plugged in infinity, well, if I'm plugging in infinity, I'm caring about the largest degree term. If I distribute this all out, I got x cubed plus some stuff. I got 5x cubed plus some stuff. The x cubes would cancel. I'd end up with a positive 1/5 in both directions. This is great, great practice. All right, I'm running behind schedule, but we can do this. Exponent rules. If you have addition, it's the equivalent of having multiplication. 2 to the third times 2 to the x is 2 to the 3 plus x. That's 4 times 8 times 2 to the x. That's 32 times 2 to the x. To a negative power, I could write this as b to the negative first to the x, which is 1 over b to the x, which means I'm taking my initial value a, I'm multiplying it by 1 over b over and over and over and over again. B is a number bigger than 1, which means I'm multiplying by a fraction, which means my function is decreasing. This is a decay. Okay. As we are decaying, though, what is our graph? Concave up. We will be approaching 0, but slower and slower and slower. My rates are going to be increasing, as in I'll go from negative 5, 4, 3, 2, 1. I'm concave up. My rates are increasing. As my inputs, increase by 2, as my inputs increase exponentially, my outputs are increasing linearly. This is the definition of a logarithmic function. Exponential functions, 1, 2, 3, 2, 4, 8. This is y equals 2 to the x. If I flip them, 2, 4, 8, 1, 2, 3, this is the inverse. We talked about inverses undoing. Boom. You kind of know if this is 2 to the x, and then you flip-flop the points, then they must be inverses of each other. Well, the inverse of 2 to the x is log base 2. So, seeing inputs multiplying by numbers, outputs increasing linearly, logarithmic. Boom. I have to multiply by 4 my inputs to increase by 4. We are literally talking about a logarithmic where if I go from here times 4, increase by 4. This one's it. If my outputs multiply by 4, sorry, if I multiply my input by 4, my output should be added by 4. Corresponding input is 4 times greater. The output is increasing by 4. It's going to be B. I got this 0.22. I got this 0.86. Multiply by 4, add by 4. I can't do 1. I can do like 1.5 times 4. 6. 1 goes to 4. Yeah, that's close. Log functions look like that. What am I doing? Taking your y's, multiplying by -3, then adding 1. I'm reflecting them vertically and shifting them up. We're going to end up looking like that. So as I get close to 0, I'll be up towards positive infinity. As I go towards infinity, I'm going to get smaller and smaller and smaller. I'm going to go towards negative infinity just slowly. Log properties, addition is the same as multiplication. So I'd multiply these two inside this log base 2. When does that equal 3? I have log base 2 equals, I think you guys already forgot about solving these equations. How do you undo a log with an exponent? I take 2 to the power of both sides. I get x squared minus 2x equals 8. X squared minus 2x minus 8 equals 0, which is x minus 4x plus 2. My solutions are 4 and -2. However, I'm not allowed to plug in a negative value into a logarithm. It's not defined, so my solution is just 4. When does log base 4 of 16 over x equal 5? I'd start out by taking 4 to the power of both sides. Oh, wait, what? They don't want me to do that. You can start out by using the log property to get this. I can then use the change of bases to say this is natural log x over natural log 4 if I wanted to. Because what I can do here is log base 4 of 16 is 2. Subtract 2 from 5. I get 3. I could then multiply by negative log 4. Boom. Solve for x by taking e to the power of both sides if I wanted to. I don't know why you'd want to do that, but it's just one way to do it. Rewrite g in form of 7 to the c, where c is a constant. Okay, so this is 7 cubed times 7 to the 4th, which is 7 to the 7th over 7 to the 6th. That means that's the same as 7 to the 1st. Rewrite this as the natural log of a plus b times the natural log of x. I could just rewrite this as 8x cubed, which is log 8 plus log x cubed, which is log 8 plus 3 log x, using exponent properties. When does j of x equal 5 to the 16th? Well, I got 5 to the x cubed times 5 to the 5th. When does that equal 5 to the 16th? This is 5 to the 3x times 5 to the 5th. When does that equal 5 to the 16th? This is 5 to the 3x plus 5. I can take the log base 5 on both sides, or just understand it's all about the exponents. I will subtract 5 divided by 3. get 11/3. When does k equal the natural log of 8? Use exponent properties to simplify. I get log x squared over 2x equals log 8. I can then take e to the power of both sides. I don't want to get rid of an x that removes a possible solution. Sometimes, though, it'll be fine, actually. So if I take e to the power of both sides, I get x squared over 2x equals 8. That means x squared equals 16x. Move everything onto one side. X squared minus 16x equals 0. X minus 16 equals 0. X equals 0 or 16. I'm not allowed to take the natural log of 0, so the answer has got to be 16. When does this output 0? This is 2 to the 2x minus 7 times 2 to the x plus 6. When does that output 0? This is not the way you do it. This is actually a tricky question. I've seen this before. You got to realize what this looks like. This looks like x squared minus 7x plus 6, which factors to be x minus 6, x minus 1. This is a tough question, which means this turns into 2 to the x minus 6 times 2 to the x minus 1. Really, the questions are, when does 2 to the x equal 6 and when does the 2 to the x equal 1? That's when x is the log base 2 of 6, and that's when x equals the log base 2 of 1. Log base 2 of 1 is 0. So I have two solutions, log base 2 of 6 and 0. I'm allowed to have 0. That's 2 to the 0, 1 minus 7 plus 6 is 0. So 0 and log base 2 of 6. Cool. 10 more questions. If you are an odd function, opposite x's yield opposite y's. That works. If f of 3 equals 0, you got the point 3, 0, and you are shifting things right 4. You're using the inverse on that inside. That means g's got the point 7, 0. Take the x and add 4. Don't adjust the y. G's got to have the point 7, 0. If the inverse function has a point n4, then the original function has to have the point 4n. What is the original function's y value when the x value is 4? 6. If you have g of x over 2, the transformation is a horizontal dilation by a factor of 2. You will take your x's and you will multiply them by 2. This is the inverse of that inside. We'll map to points we know. If the domain of my original function is negative 6 to 12, the new domain of my transformed function will be those x's times 2. I see my y's are increased. I see that my x's, so my x's go from 4 to 2, 2 to negative 1. So my x's are being multiplied by 1/2, which means I need a 2x on the inside. And I'm taking 2 to 5, like my y's must be multiplied by 5. I think it's got to be that. No. Hold the phone. This point here, horizontally shifted over, comes here. But then times a number does not move that one down. That's not right. There has to be some sort of shift going on. Same here. I multiply this by a half. I must be subtracting 1, multiplying by 5. Or 3. Oh, so multiplying by 3, then subtracting 1. That works out. Multiply by 3, subtract 1. Multiply by 3, subtract 1. This, that. That's a good question. Okay. All right. F of 2 is -1. G inverse of -1. That is the inverse of G. Just to make sure you guys know, if G's got the point AB, G inverse has to have the point BA. G inverse of -1, I'm looking for G's y coordinate, that's -1. 10. Almost there. F inverse. All right, let's look at some points. 1, -1. That means that the inverse has to have the point -1, 1. Okay, it's between these two. What's another point? -1, -2. That means the inverse has to have the point -2, -1. That. Ooh. G of 1 is 2. F of 2. F of 2 is 3. F of 3 is 4. F of 2x is composing F and G. Would be a horizontal dilation by a factor of a half, which means I'm taking my x's and multiplying by a half, which means 4, 0 goes to 2, 0. That's that one. If G is the inverse of F, G of x has to be 2 to the x. When does G equal 8? That's x equals 3. Zero, 1, 1, 4. Oh, okay. This is the log function. Times 4, add 1. Times 4, add 1. 216 must be on the graph of the inverse, because 16.2 is on the graph of this. Oh, we did it. Time. 53 minutes. Okay. I'm going to say if you skip the unit 0 questions, you can definitely get this done in a 2-minute per question pace. You got to know what you're doing, and a lot of you are going to forget the rational functions unit. I can tell. And a lot of the exponential functions unit. Hopefully you remember. Yeah, the rationals and the exponents are the ones that you're probably having the most difficulty with. You'd had the most difficulty with on the test. So if there's time I'm going to spend during class, it's going to be on those. But you got to remember everything, which is why we're going to go over everything. In the Schoology folders, you got lots of resources. Go over the stuff that you're bad at. All right, I'm out.